Degradation of magnetic properties of non-oriented silicon iron sheets due to different cutting technologies. Non-oriented electrical steels have a crystalline texture which is characterized through a very low magnetocrystalline anisotropy. They are intensively used in the manufacture of the high-efficiency electrical machines in order to save energy and to avoid the overheating phenomenon. It is well known that the electrical machines have an energy consumption of 50% from the worldwide electricity consumption, and almost 6,040 megatons of CO2 emissions are due to these devices. According to the newest regulation, it is expected that in 2030, without proper environmental decision, the energy consumption to increase very much and the emission will be higher than 8,000 megatons per year. Recently, the energy losses of the newly produced electrical machines have been decreased with an amount of 20% by comparing them with those measured before 2016. The most important machine producers made motors in classes of premium efficiency i.e. 3 and above, super premium efficiency i.e. 4 and ultra premium efficiency i.e. 5. Nowadays, it is a great challenge to produce an efficient electrical motor because thermal stresses, insulator aging, and low energy losses have to be taken into account. Usually, the magnetic cores of the electrical machines are prepared by cutting the non-oriented alloys through mechanical punching because this method is very fast and cheap, although it generates inside the material mechanical stresses that affect the energy losses and the magnetic properties. A work hardening phenomenon is expected to appear at the cut edge and the formation of the crystalline grains are present. Usually, during a recrystallization process, these deformed grains are entirely transformed in new magnetic grains with better properties. The most important parameters of the cutting procedure are the clearance and the cutting angle, but also the hardness of the blade. It is usually taken into consideration. When it is chosen a proper value of the clearance, the induced mechanical stresses are minimal, and this fact contributes to the life increase of the cutting shears. A good quality cut edge is obtained based on the empirical determination for each cutting machine. When a strip is cut, only a small part is cut and the rest is separated through fracture phenomenon. The samples involved in the paper were prepared using a classical computer numerical control two-rate punching machine. This device has a 3-axis Siemens special CNC system and uses AC servo motors. Its main components are actioned pneumatically and it is equipped with concentrated lubricating systems which decrease the friction during the cutting procedure. Sometimes the electrical machine's producer want to obtain a free bar cut edge and they choose the non-conventional cutting technology as laser. Laser method is a very flexible one, but unfortunately it induces important thermal stresses and the method is expensive. In the case of CO2 laser, the single generated wavelength is in infrared spectrum. The beam has a 0.025 mm diameter when it travels from the laser resonator to the beam path. It is guided through a mirror or a special lens system and finally is focused on the material. The laser beam is accompanied by a compressed gas as oxygen or nitrogen. The cut edge is almost perfect, but the high power density of the beam has an unwanted result, which consists of a rapid heating, melting, or partial vaporizing of the material. In the paper, a Morn laser machine was used to cut the samples. This machine is a very performant one, and the laser cut has no cracks or supplementary deformation due to the thermal stresses, and it has a very high stability of the cutting tool. Other non-conventional cutting technologies are the electroerosion and water jet methods. The electroerosion produces any stresses, but the process is very slow and it can be used only for small dimension electrical machines. Today, EDM machines are very stable, starting with 1980 due to the introduction of the CNC in the EDM technology, and they could be used to cut complex shapes. The basic phenomenon involved in the electroerosion cutting procedure is the energy transformation from electrical into thermal energy using a series of electrical discharges that appear between an electrode and a workpiece introduced in the dielectric fluid. This fluid is a very special one because it has to avoid the electrode electrolysis. The EDM procedure is a modern technique based on material erosion when a spark appears as a result of an applied voltage between the electrode and the material surface. The dielectric fluid is a cooler medium and it helps the discharge energy to be concentrated on a small area. As the erosion advances, the electrode is moved through the dielectric fluid. Recently, servo systems are used to assure a constant gap voltage between the material and the wire and to retract the electrode when a short circuit occurs. A kindred wire EDM controlled by a CNC system which utilized brass electrode wire and high-frequency impulses was used in the paper. This machine is very suitable for cutting materials with high precision. The water jet leads also to a very good quality of the cut edge, but special expensive equipment is needed and the cutting speed is relatively slow. Abrasive particles as garnets are used and the price of the cutting procedure is very high. The abrasive particles do the material cut through a sawing action and it leaves a precision cut surface. This method is suitable to cut almost any type of steels and it has a narrow curve width. Physical properties such as melting point, thermal and electric conductivity density have a limited importance, although the hardness of the material could reduce the cutting speed. This process induces no heat-affected zone and no hard oxidation layers on the cut edges, which could lead to the microcracks apparition. This technology damages minimal the magnetic properties of the material due to the plastic deformation. An OMAX water jet machine was used. This device performs a very high accurate edge cut and it uses garnet, as I said before, as abrasive particles. Materials and methods. A medium quality commercial non-oriented steel M865A was investigated. The material properties and the geometrical parameters are shown in Table 1. The magnetic measurements were done by using an industrial Brockhaus single strip tester with a double C yoke, which is a standardized device, and it controls at each step the measurement, the form of the secondary voltage in order to be a sinusoidal one. This device permits the measurement of the energy losses and of the relative magnetic permeability with its component, real and imaginary parts. An external magnetic field is applied and the magnetic flux is generated into the tested sample. The current in the magnetizing coil is determined with the help of a shunt resistor. The magnetic path length between the polar pieces is 240 mm. Along this path are placed the measuring and the magnetizing coils. A sample of minimum 280 mm length and a maximum 30 mm width could be investigated. The influence of the cutting procedure on the energy losses was analyzed using the energy loss separation method. According to this theory, the total energy losses are divided into hysteresis, classical, and excess energy losses. The hysteresis losses are due to the pinning points and impurities that are present in the medium quality, non-oriented steels, and they are usually analyzed by taking into account the coercitivity mechanism. They can be computed by extrapolating in zero the measured total energy losses. The classical energy losses are generated by the eddy currents and the material is treated as a homogeneous medium. They can be computed with the following formula where D is the sample thickness, sigma is the electrical conductivity, rho is the non-oriented steel density, and F is the experimental frequency. The excess losses are due to the microeddy currents which are formed in the vicinity of the domain walls. They are computed by subtracting the classical and hysteresis losses from the total energy losses. Results and discussions. The normal magnetization curve defined as a geometrical place of the symmetrical hysteresis cycle peak points which extends from the demagnetized state to the saturation is presented in Figure 1. In order to experimentally determine the normal magnetization curve of the samples, measurements were done at the industrial frequency of 50 Hz. In the case of each sample, symmetrical hysteresis loops were determined at different peak magnetic polarizations. The electroerosion and water jet technologies determined an easier magnetization of the material because the cutting procedure induces any thermal or mechanical stresses. The punching and the laser procedures leads to a more difficult magnetization process due to the generated stresses. In Figure 2 is presented the variation of the total energy losses as a function of the frequency for three values of the peak magnetic polarization. At 500 millitesla, the water jet technology leads to the lowest value of the total energy losses, followed by the punching method, and the highest energy losses are measured in the case of laser. These observations are valid also in the case of 1000 millitesla, but for 1500 millitesla, the lowest value of the energy losses is determined for the electroerosion technology. It can be noticed that with the increase of the peak magnetic polarization, the influence of the cutting technology on the energy losses is reduced. The hysteresis energy losses are invariable with the frequency and they are a direct consequence of the magnetization processes, which are due to the magnetic domain wall movements. It can be observed from Figure 3 that the most important variation of the hysteresis energy losses is noticed for the high magnetic polarization domain, especially in the case of punching and laser. The lowest value of the hysteresis energy losses are determined for the electroerosion and water jet cutting technologies. The classical energy losses are generated by the eddy currents and they are directly proportional with the peak magnetic polarization and the frequency. It can be noticed that from a specific value of the frequency, these losses become predominant with higher value. The excess energy losses are influenced by the cutting procedure in the case of all the peak magnetic polarization values. The water jet technology leads to the lowest value, followed by the laser and electroerosion procedures. The mechanical punching has a strong influence on the magnetic domain structure and is directly linked to the existence of higher values of the excess energy losses. The relative magnetic permeability is a physical quantity which describes a material property to concentrate the magnetic field lines where an external magnetic field is applied. A magnetic material is more adequate to be used in industrial applications in the case of high values of magnetic permeability. In Figure 6 is presented the variation of the relative magnetic permeability for two peak magnetic polarizations. It can be noticed that the magnetic permeability presents an inversely proportional variation with the frequency. The influence of the cutting procedure is more pronounced for frequency values lower than 100 Hz. The highest value of the magnetic permeability is obtained for the water jet and electroerosion technologies. Conclusions. The cutting procedure damages the magnetic material microstructure more pronounced in the case of laser, followed by punching, electroerosion, and water jet. To reclaim the initial magnetic properties of the alloy, some thermal recrystallization treatments are required, but this step is not taken into consideration by the electric motor manufacturers because it damages the insulator layer that covers the magnetic core sheets. The use of water jet or electroerosion technologies that have a reduced impact on the energy losses and the relative permeability is taken into consideration only in the prototyping and special cases because of their slow cutting speed. As a compromise between cutting speed and the induced damage on the magnetic properties of the electrical motor manufacturer, they still prefer the classical mechanical punching.